Yeah, yeah.
You go over the idea that just 23 on 15.1 multiple choice.
15.
No, 23. 15.
Numbers.
Multiple choice problem 23 from the first chunk. A block attached to a spring, blah blah blah.
Because I did it and I got 12.5. Like I tried doing some math.
Oh, I wonder if I made a mistake.
No, I got it right.
Okay.
That means it's definitely right.
All right. So 23. It says a block is attached to a spring. It undergoes simple harmonic motion on a horizontal frictionless surface. So you should be picturing that, except it shouldn't be floating, and then it's oscillating back and forth. Let's see. The total energy is 50 joules. So automatically you should be equating a couple things to that 50 joules. Maximum kinetic energy and maximum potential energy, right? So our maximum potential is equal to our maximum kinetic is equal to our mechanical energy, 50 joules. All right? Then it says when the displacement is half of the amplitude, what's the kinetic energy? So the idea is 1/2 k times xm squared. Remember, xm is your amplitude. That's 50 joules, right? Good. So that's U max, right? So if we're at half of that amplitude, so at 1/2 of xm, then our potential energy ought to be 1/2 times k times 1/2 of xm squared, right? All right, so what's that going to give us, you guys? Even going to 1/8, you're making it harder than you need to. Even going to 1/8 is making it harder than you need to. By chopping this distance in half, remember it's getting squared, right? So this is the same as 1/2. Oops, darn it, sorry. This is the same as 1/2 squared, so that's that, right? Times what? Times 1/2 k times xm squared, right? Does that make sense? What is this? What I just wrote in blue, what is that? That's the maximum potential energy, right? Does that make sense? So it's a quarter of that. So that's a quarter of 50, 12.5 joules. So that's the potential energy, but the question doesn't want to know the potential energy, it wants to know the kinetic. So how much kinetic energy do we have so that it adds up to 50? 37.5, right? Did I say the answer is C?
Yeah.
Yeah.
And no,
It is. Oh, no, it's D.
in a different question it says explain why it is half. So
Oh yeah, it's totally D. When the displacement is half of the amplitude.
That's really awkward.
So to this point, go on the AP test.
Yes, I'll write the college course. Hey guys, listen. Here's
I screwed up.
I made my.
It's me.
All right. Yeah. So you're totally right. So the answer to that should be D, not C.
what I said B.
Wow.
Next,
This is actually right.
Yeah.
So I found A max, which was 50, but I didn't use numbers at first, which is 1/2 mv squared, and B max isn't it omega x max? Not omega B, weird.
Yeah. No, that's right. Omega times x max. Yes.
And so then I went to like when x is half, so I did x max over 2, keeping the same W thing, and then squared it and then put them over each other, and I got 1/4. With 50 is 12.5.
Yeah, that's weird.
Why?
is what he said, right? Because I lost your train of thought.
Oh, I have no idea.
All right, so you're saying you solved it using this. You said that v is omega x, right? Okay, but what that equation gives us is that the maximum velocity is the same as omega times the maximum displacement. But they don't occur at the same point. Do you know what I mean? So this is true. That is not. Do you understand the distinction? And I'm worried, and I didn't hear exactly what you said. I lost your train of thought because you went through it too quick. But I feel like you used this.
Yeah.
Is that what happened?
Yeah.
Okay. Good. So it works for acceleration. This is a true statement. At any point, yep. But it does not work for velocity. Good or no? Okay. Do you want to know why? It's because when you take your first derivative, you get a sine. When you take your second derivative, it brings you back to cosine again. All right. Are we good? Ish. Okay. What else? Let's stick with chapter 15 right now, and then if we have time, we'll go back and finish that first FRQ from Friday.
Could you do one on the questions?
Yeah, what do you got? Oh, problem number 1. I got you. I'm sorry. I misunderstood. Okay, let's see. So which of the following describes phi? What is phi again, you guys? The phase shift, right? So which of the following describes phi for the simple harmonic motion shown in figure A at the right? So here's figure A. We got two graphs. There's a position time graph that looks like this. And there is a velocity time graph that looks like this. Oh, no. All we need is the first one, sorry. Okay, so this has been shifted. So a regular cosine, so if phi was 0, it would look like this, right? So it looks to me like this thing is being shifted to the right by a distance of what? More than pi over 2, right? Because this would be pi over 2, right? Does that make sense? So it looks to me like, and this is just my knee-jerk reaction, I'm going to look at the answers, because I actually can't remember. But it looks to me like phi needs to be somewhere between, it's greater than pi over 2 and less than pi, right? Because you haven't gone a full... Does that train of thought make sense? All right, so, let's see, that's not one of my choices, though, is it? So remember, you guys, when you do phase shift, anytime you shift over by 2 pi, that doesn't change it, right? So you can always either add or subtract multiples of 2 pi to phi, and that doesn't change it. Does that make sense? So none of these answers show up on my choices, am I right? So let's try subtracting 2 pi from both of these. Because it looks like all the answers here are negative, right? Well, it's clearly not B, right? B doesn't work. So let's see if either A or C works. If I subtract 2 pi from this, this gives me negative 3 pi over 2 and negative pi, right? Is that one of my, yeah, that's choice C. So I like choice C. Is that the right answer?
It's A.
What?
Yeah, I put C.
Wow. Well, my physics teacher sucks. That's you talking about me. Which of the following describes phi for the simple harmonic motion shown in figure A? Why does my answer not work? Oh, right, because if it's being... Oh. Sorry. I got enough minus. I'm really sorry, you guys. Let's rewind. My original logic was good. Yeah, I know you guys are gonna rack up some points today.
You did that on purpose, didn't you?
All right, let's try this again.
That's just nothing but extra.
Points are points. So I'll give you your points. What did I do wrong here? Anybody see it? Anybody catch it?
It's positive.
Right, it's negative.
Yeah.
We're shifting to the right, so these have got to be negative values, right? So that means that choice A is right, because that's exactly, oh, I gotta flip my alligators around, right? You're welcome. All right, so everybody good with that? So that's choice A. And then choice B is attained by, I think just by adding 2 pi. Yeah, exactly. Yeah, if you add 2 pi, you get choice B. Okay, so I forgot the negatives. That was why I got that wrong. All right. Are we good? All right. Now, what I've seen, and so the process of going through these multiple choice questions and doing some of the FRQs has led me to, like, next year I want to assign this again. This is really more mathy than physicsy. You know what I mean? I haven't seen anything like this on the AP tests. So that's next year I'm going to weed out a lot of the stuff that I think leans in the direction of math and less in the direction of physics. So, yeah.
Degrees of radius, physics, it doesn't matter.
What do you mean?
Like, our answers, we come up with response.
I would do radius. Hey guys, you're not. You're making me nervous. Thank you. I saw a guy break his arm wrestling once, so I'm really squeamish about that stuff. Right here.
That sounds awful.
It was horrible. It just like it was like, oh, let's call 911. Yeah, right up here. Yes, I would do radians. Okay. What else, you guys? Oh, one other quick thing you guys have been asking about. I finally found this in print. Significant figures are a non-issue unless you write down like a billion digits. You know what I mean? So use a little bit of common sense. I think what I saw said something like anywhere between 2 and 4 significant figures is reasonable. Cool. So, all right. What else we got from 15? Yeah, so.
15.34, number 13 and 11.
Number which one?
13.
13 multiple choice, rotational inertia, that one?
Yep.
Okie dokie, here we go. So, so this is 15.3 to 15.4, number 13 multiple choice. All right, so it says the rotational inertia of a uniform thin rod about its end is ml squared over 3. So that's a uniform rod about its end. Where m is the mass and L is the length. Such a rod is hung vertically. Oh, I can do it? Oh, no. No, darn it. Sorry. Such a rod is hung vertically from one end and set into a small amplitude oscillation. If L is 1 meter, this rod will have the same period as a simple pendulum of length, blah, blah, blah. Okay, so we learned about, I guess, 3 or 4 different types of pendulums, right? Torsion pendulums, physical pendulums, simple pendulums. I feel like I'm missing one. Maybe that is it. What's this? It's not simple. So simple would be only if all of the mass was concentrated at the end. Sorry, I'm looking for a meter stick. So this is it's called a physical pendulum, right? Where not all of the mass is at the end. Cool? So, and I gave you guys the equation for the period of a simple pendulum. It was T equals 2 pi times the square root of I over mgh, where h was the distance from where to where? From the pivot point to the center of mass, right? Okay. So, is that where your problem was? Okay. So find your period where h here is going to be 0.50 meters. Good up to there? Anybody need me to say more about that part of it? I don't remember what that turns out to off the top of my head, but that's going to give you a period. And then you set that equal to, and solve for alpha. Cool? Cool, you all set? Alrighty. What else, you guys?
Over in 15 degree, can you do,
That's a good one. Like, to me, that's a
70.
70, problem 70. Holy cats on the back. Oh, yeah. Hmm.
Yeah.
Okay. A couple people have. All right. A wheel is free to rotate about its fixed axle. A spring is attached to one of the spokes a distance r from the axle as shown in the figure here. So we got a little drawing. Let's see if we can reproduce this real quick. So here's the wheel. Here's the center of the wheel. We've got two radii. There's lowercase r and there's capital R. And the spring is attached to this point here, right? So it says, assuming the wheel is a hoop, of mass m and radius r, what is the angular frequency of small oscillations in terms of, and make sure you're careful about this, you guys, when you solve these problems, you got to make sure you just use the variables they allow you. So here are the variables we're allowed to use. Mass of the wheel, radius of the hoop, the radius from which the spring is attached. I said that awkwardly, but you know what I mean. And the spring constant. So those are our variables. So here's, I think, the tricky part of this problem. We're given a spring constant, that's a linear spring constant, right? But that spring constant is being used to produce a torque, right? So what I need to do is somehow find a way to think of this, really this is a torsion pendulum, right? You guys see that? Right, because the wheel's going to go womp, 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 right, back and forth, right? So remember, ooh, somebody just beat. Okay, so I guess here's what I'm thinking. I probably should dig out my notes before I go too far down this rabbit hole and make sure I'm not steering us in the wrong direction. But off the top of my head, without looking at my notes, I think that the direction we need to go to do this is as follows. So I know one of the equations we learned was that omega is root of m over k for a regular spring oscillation, right? Okay? But the problem is, here, that's not really what's going on here, right? Because the whole mass of the wheel isn't oscillating back and forth, right? In fact, the middle point isn't oscillating at all, right? All right? So really what I think I want to do is I want to come up with the torsional counterpart for that, which is this, I over kappa. And the problem is we don't have a kappa. You guys see what I'm saying or no?
Yeah.
All right, so well, let's see if we can come up with a relationship. So check it out. So I know that K is the amount of force needed to stretch a spring a certain distance x, right? And similarly, kappa is the amount of torque needed to twist your thing through a change in theta of theta. Right? So I know I just need to find my kappa. All right, well, let's do this. So let's see if we can come up with an expression for the torque being produced. Okay? The torque being produced, describe to me the force that's producing the torque. It's the force of the spring, right? So this is the force of the spring times the distance we've stretched it, right? Divided by theta. Well, if I stretch for small angles, if I stretch the spring a distance of x, then my theta ought to be x over r, right? Sorry? It's a jumper equation that we learned. X is theta r, right? That's one of the jumpers we use. Does that make sense? Everybody good? All right, so we're getting there. I'm glad that 7 days before the AP test we're. All right. All right. So what do we got, you guys? So if I simplify this, doesn't this give me Fs? The x's cancel times r, right? Oh, but what's Fs? That's that's kx. What did I do? Oh, this is wrong. Sorry. Sorry, I messed up. We're trying to find torque, so it's the force of the spring, not times x. It's the force of the spring times little r, right? So if you simplify that, so you get that kappa is Fs r squared over x, right? Does that buy me anything? There you go. Thank you. And Fs is kx. Over x. The answer is cancelled. So kappa is k times r squared. Thank you. All right. Good with that? All right. So now we can plug our stuff in over here, right? So now we can go, oh, well, omega is I, which is, what was it, 1/3 mr squared?
Yeah, it's 1/3, definitely 1/3.
Is that right? Okay. M times capital R squared, right? Over kappa, which is K times R squared. I guess that's it, right? So omega is, if you bring the 3 down, M R squared over 3 K little r squared. There you go. Oh, squared.
Is it K over I?
Yeah, also you have to
If it was K over I with no 1/3, then it's
Number 70. I remember 5 minutes ago when I said I should check my notes before I go too far down this rabbit hole.
I thought hoop was just one. Well, it says
Oh,
well, yeah, but all the white particles are at the same rotation from the center.
oh yeah, it's just mr squared. Yeah, it's a hoop. I was mixing it up with the previous problem.
Yeah.
Yeah, so there's no 1/3 in there, so we're good.
So is it I over K or K over I? Or kappa over I?
Yeah, because the answer has.
And here it's KR squared.
Oh, did I wrote? Oh, shoot, it's period that's I over K. Damn it. Yes, it's totally K over I, and that fixes everything. Sorry, you guys. Wow. Sorry. It's 3 points in a couple minutes.
No, that wasn't the point. It's right on the sheet.
No, there, oh yeah, it's right.
It's right on the sheet. You
Yeah.
guys.
Right, but it would be nice if, a week before the AP test, I was showing you how to do the problems, right? So. All right. So, yeah, so there were 2 little issues there. The first one was just that I was thinking, I forgot that it was a hoop. I was still thinking about the last problem where it was a rod. So it's just mr squared. So that clears up the 1/3 issue. And then I've got my equation for omega. This is upside down. It's k over m and k over I. Sorry about that. Okay, so anyway, the big premise behind it, apart from the fact that I had those flipped over, I think the big thing is, do you guys understand why I had to convert this all to being torsional? I think that's the big thing that I want to make sure you guys understand. Okay. And the brief answer is that the whole wheel isn't oscillating linearly, it's rotating rotationally. In a terrible sense, but you know what I mean, right? Cool? All right, cool. Sorry about the glitch there. Okay, what else?
What does B mean?
What does B mean?
Question mark.
Oh, that is a typo. It's supposed to be capital R. I don't know where the capital R went. So what is omega? That's, yeah, so the bottom one says, C says, what is omega if R is 0? The one above it was supposed to be, what is omega if R is capital R? So it's basically just asking you the two extremes, right? The spring could be either attached at the middle or at the outer edge. So it's just asking you to check the two possibilities. So if R and R are equal, then you just get M over K. If R is 0, then your period is infinite, right? Because it's not going to rotate at all, right? Because there wouldn't be a torque produced if it was attached to the center.
Wouldn't it be 0?
Yeah, because those are flipped.
Oh, because it's upside down, right? Period would be infinite. Oh, having a rough day, aren't I? Okay. Good? Okay, cool. What else, you guys? What do you say?
42B.
42B? Alright, suppose that a simple pendulum consists of a small 60-gram bob. I always picture a little dude named Bob every time I read this. No. Very small one, then. It's only 60 grams.
Wow.
12 nickels worth of bob.
Gotta go to the gym.
Yeah, yeah, right. Or yeah, or eat some protein, something. Okay, so a small bob, 60 grams, at the end of a cord of negligible mass. If the angle theta between the cord and the vertical is given by that expression there, then what is the length? Okay. Okay.
Which question is this?
42.
Number 42.
I got A, but yeah.
Okay. Does anybody want me to go through A?
I do.
Yeah. Okay, so here is what we know. We know that the mass of this thing is 0.060 kilograms, right? And we know that it is going to oscillate following simple harmonic motion at a rate of 0.08 times the cosine of 4.43 t plus 5. Cool. And we need to find the pendulum's length, and we need to find the maximum kinetic energy. Okay, so the fact that it's a simple pendulum tells us that we automatically know the period is this, right? And there's something else up here that tells me something about the period.
Oh, wait, oh, yeah.
Yeah, we know omega, right? So remember, omega is 2 pi over t, right?
Okay.
So that means that t is 2 pi over omega, right?
Yeah.
So this is 2 pi over 4.43. Aha, the 2 pi's cancel and solve for your up.
Okay.
Cool?
I was just confused, yeah, because the equation was like inverse, so I was like, I don't know what to do.
Okay. So, yeah, so that was what I was saying before, is that the fact that it's angular doesn't change it at all. This is still an omega exactly as if it was linear.
But I thought that was for like torsional pendulums.
You can argue that a simple pendulum is torsional because there's torque applied to push it back to the center, and when it's at its center point, the torque is 0, right? Because
Okay.
The force and the lever arm are parallel.
Yes.
And in fact, this is not me trying to throw salt in your wounds, but like when we derived this equation, the first way we did it was by assuming that it was torsional. So I know that's, and it's weird, it's counterintuitive, but. Okay, so anyway, so solve this, and the L turns out to be, what did we say, 0.499 meters?
Yep.
Okay, so that's that. Okay, so then the next part, part B, says, what's the maximum kinetic energy? Well, I guess there are a couple ways we could go about this. I guess one option would be to try to think of it as a torsional pendulum and find your kappa, and then do, so usually use 1/2 k x squared. So for us, it would be 1/2 kappa times theta squared, but we have to find our kappa. So I guess we could do it that way. Let's see, what did we decide kappa was? It's I omega squared, right?
Yeah.
So let's see, we know our I, and we know omega. So that would work, that would be a way we can do it. So what is I for a simple pendulum, you guys? R squared, right? So for us, it's 0.06 is the mass. What would I use for my radius? Yeah, the length. So there's our I, and we know omega is 4.43. So then just plug your numbers in, right?
The, thing square. Theta.
Mm-hmm.
Should do that too. You just plug in the kappa. It's still 1/2 kappa theta squared.
Say that again.
If we're trying to find the potential energy, it's 1/2 kappa theta squared.
Mm-hmm.
So what do we do with theta squared?
Oh, what do you use for theta?
Yeah.
We're trying to, okay, good, gotcha. We're trying to find the maximum potential energy, so we would use the maximum theta. Do you see, maximum theta is written up here somewhere. The trick is, where the bleep is it?
That would be 0.08.
Exactly, yep, yeah, so here's our, just trying to underline it, right? Yeah, so there's our maximum theta. Follow? All right, the other way you could do this is take the derivative of this expression to find omega, and then find your maximum kinetic energy, doing 1/2 I omega squared, and then just know that your maximum kinetic and your maximum potential are equal.
That would be capital.
Yes, it would.
I
Yeah.
use like the V max.
I know.
It was like smaller omega theta max, but
Say that one more time.
I tried to use the V max or velocity maximum. What's the omega the small one times theta maximum? But does that not work because we're in a different sort of pendulum?
Yeah, it's angular, so that was exactly what Alex was just saying, was that it's not V max, it would be capital omega max, right? Do you see what I mean? Because, yeah, do you see why? Are we good, you guys? Yeah, I hear you, I hear you. What else, guys? Yeah, cool.
Could you explain why for
Oh, real quick, my answer to 42B, meters, that's totally wrong too. That's got to be joules. Kinetic energy? Jesus. All right. Well, there you go. Sorry, what were you saying, Philip?
for the first section of questions,
Okay.
number 9, why B is an infinite period?
And then what?
9 on the first.
It's because, so if I do this, just realize this is wooden, not plastic. Sorry. If I do this, the center of mass is below my pivot point, and so gravity produces a torque on it that causes it to oscillate, right? Okay? If you pivot it at the middle, technically speaking, if this was frictionless, there's no way I can possibly do this, but if I spin it, whoops, theoretically it should just keep spinning forever, right? Okay? So there's never a point at which it's going to stop and, you know what I mean? It's not going to oscillate. It's just rotating, right? So the time that it's going to take before it stops and goes back the other way is infinite, because it's never going to stop. Does that make sense? What else?
For the, okay, wait. For the period of not a simple pendulum, but the other one.
Physical pendulum?
Yeah, that's that 2 pi times the square root of what?
I over mgh, I think.
Yeah, so so that makes sense. That's why it was infinity, because then if you're h
Ah!
0, it's, yeah.
Nice, I like that. Do you see what he's saying? The distance between your pivot point and your center of mass is 0. Exactly. Yeah. And that was why a minute ago I said infinity and it was really supposed to be 0. That was what I was thinking. But I got my period and my frequency.
So that t equals 2 pi times the square root of L over g, that's only if the mass is concentrated at one point.
At the end of the.
Yeah.
You good, Phil? Yep. What else, guys?
39 from 15.3.
39 from 15.3. What do we done? We got like 2 minutes here. Wow, I feel like that hour flew by. 39, 15.3. The balance wheel of an old-fashioned watch oscillates with angular amplitude pi in period 0.5 seconds. Find the maximum angular speed. Oh, yeah, I got it. Okay, so this one, I actually... So here we go. So for 39, we've got a watch wheel that's oscillating back and forth. So our maximum displacement angularly is pi, and the period is 0.5 seconds, right? So omega is 2 pi over t, right? So 2 pi divided by a half actually just gives you 4 pi. Is that okay if I leave that like that? Okay. So, well, that means that our theta at time t is theta max, pi. Am I going too quick? Times the cosine of omega, which is 4 pi t, plus some phase shift. Well, it doesn't matter, right? Because we don't actually need the velocity or the acceleration at any specific time. We just need to know the maxes, right? So what should we make our phase shift? To 0, right? Well, there's that. So now I can find my d theta dt, also known as capital stupid omega, right? So that's going to give us, well, you got to take the derivative, so you're going to get -4 times pi squared sine of 4 pi t. So what's my maximum angular velocity? 4 pi squared, right? So let's see. Oh, yeah, right, and that's what question A is asking for.
Okay, yeah, I just did that out.
Gotcha.
Yeah, I actually used the omega max because the small omega theta was set to that.
Say that one more time.
The big one, the big omega, that was the small w1 times theta max. We had that.
I think that works.
I just did my math.
Oh, okay, okay. Gotcha. So then for B, find the angular speed at a certain displacement. So you're going to set your displacement equal to that, solve for the time, and then find the corresponding velocity. And then finding the magnitude of the angular acceleration. Well, remember, alpha is just negative omega squared theta, right? That's the equivalent of A is negative omega squared x. So that's how you do C. Cool? Okay. All right, so here's the deal. I want to make sure we still spend more time on FRQ. Sorry, I know the bell just rang. Do you guys want to spend more time on 15, or do we want to just forget about it and move forward and do Okay, all right, cool. So due tomorrow is the 2012 FRQ. Do Wednesday's the multiple choice. All right? Yeah, give me what you got for the homework. I'll get them back to you tomorrow. Oh, I got you. Cool.
So I had the third I actually think I got a choice because
And that's the one we haven't gone over. We'll go over that someday later. Time.
okay, so set up with the queue on this one.
This.
Yeah, I think it's, yeah.
I recorded my notes the other day, so you can take a look. If you need more help, let me know. All right, I'll mark you down right now. Thanks, Kurt. Hey, what's up?
Still have an E for the last one, or?
I know. I realized that. I'll take care of it. It's in my stack. Sorry about that. It's totally my bad.
I wanted to know, so I said I'm including my content in the I wanted to say self-managed farm.
Sorry? Friday, 2013.
Jack, it's always been the Jack, it will always be Jack.
There should still be copies of the back here. You think you have it?
Legally, how long go on?
What?
How long do it
Okay, someone's an hour, right?
No.
Okay, Caitlin, you get 20 minutes.
take? Okay, Alex,
Yes. Yeah.
go.
Do you happen to have any?
Oh,
Go.
I'll be gone.
how did it go?
Not
So,
Yeah, this one was definitely harder than the previous one.
Yeah, it was tricky.
Oh, I see.
It's actually me and Dante.
All right. So and then on Friday, I went over this. I'm going to do this separate variables. Yeah. So if you want to watch it. So yeah. So if watching it doesn't help, come talk to me.
Okay.
Okay. And I think that class went better on Friday than it did today. But like I said, let me know if you need more help with it.
Okay, thank you.
Yeah. Thank you. Okay. All right. You were starting to ask me something.
I was just like,
Play with them.